SwayamPrabha.
Welcome. So in the last class we have finished dual fitting and we have seen a high level idea of using linear programming rounding. So in today's class we will see linear programming rounding using some examples. So our first example is set covered using LP rounding. So let's recall what was the linear programming formulation. The ILP was minimize summation of S in S, C of S, X of S. Recall XS takes value 1 if the algorithm picks it, otherwise it is 0. And the requirement, the constraint is subject to for each element. I go over the sets E in S, XS, this is greater than equal to 1. This is for all element E in U, and we have XS is greater, XS is in between, takes values in 0, 1. So this is the ILP formulation. Next we relax it, LP relaxation. Minimize summation cost of S times X of XS, S in script S, subject to summation S in script S, E in S, XS greater than equal to 1. This is for all E in U. And I want to write, I relax this integrality constraint of XS and allow it to take values greater than equal to 0, less than equal to 1. But because we are minimizing it and the requirement is to pick one set to cover each element, so we can safely delete this constraint. Recall that this constraint was or cannot be deleted for set multi-cover because it may be beneficial for cost, minimizing cost, to pick same set multiple times. So because our problem requires has a constraint that each set can be picked at most once, so that constraint needs to be kept explicitly, because there for set multi-cover it may be beneficial for pick a set more than once. because of the coverage requirements. Here it does not make sense to pick any set more than once. Okay. So then what we do is that we solve LP let XS S in this be an optimal solution to the optimal solution of the LP relaxation. Now the final step is to use this solution to cover or to construct a integral solution. So because this is a solution, so we have opt is of course greater than equal to LP opt, and LP opt is summation for this solution summation XS summation CS times XS S in script S. Now we construct an integral solution of the relaxed LP. Okay, and this is the most non-trivial step of this entire process. The step till now is sort of mechanical, it's always there. So you start with a solution which is a fractional solution of relaxed LP, and how you can use that to construct a integral solution for the linear program. So for that there are various methods. One is often you need to understand the structure because of the problem. Is there any special property of that this solution satisfies, this fractional solution satisfies, and this is what we will see now. So for that let F be the frequency be the maximum frequency of any element. What does that mean? That is, every element is present in at most F many sets in the input. So with this we claim Now look at the constraints. For every element E in U, there exists a set S in script S such that 1. The element E belongs to S, and 2. X of S is greater than equal to 1 over F. Proof. So let E in U be any element so for U we have a constraint. What is that constraint? That summation sum over sets S in script S, E in S, XS greater than equal to 1. X XS is greater than equal to 1. Now this sum contains at most F terms, and they sum up to at least once, hence there exists a set S in script S such that 1. This element E belongs to S, and X of S 2. X of S is greater than equal to 1 by F. Okay, now with this claim at hand we will round it. So what is our rounded solution? X we define X S prime to be 1 if X S is greater than equal to 1 by F and 0 otherwise. This we define for all set S in script S. So observe that X prime S in script S is a solution of the ILP. Why? That is because, so let us see, so again we need to claim that this is a solution to the ILP. Why? Because this is follows from previous claim, this is follows from the fact from the claim that for every element E in U, there exists a set S in script S such that this element E belongs to the set and x of S is greater than equal to 1 by F. Hence, for every element E in U, there exists a set S in script S such that E belongs to S and x prime S equal to 1, and this is exactly the requirement in ILP. Okay. So now next what we need to do? Next we need to prove approximation ratio. Approximation ratio of the algorithm. So what is alg? This is the value of the objective function here at solution x prime S. This is summation C of S x prime S in S. Now observe that okay. So here is the thing, theorem. We need to compare this with opt is greater than equal to summation C of S xs S in script S. So claim the above algorithm is a F factor approximation algorithm for set covered. Okay, proof. So let C subset of S be the collection of sets picked by the algorithm. So Consider any arbitrary element E. So first, from our argument before, from previous claim, it follows that C is a set cover for U. This we have argued here, that it is a solution to ILP because it is a solution to ILP. Now the rounding process, so now we need to compare ALG with this. So what is ALG? Let us see, ALG is summation S in script S, C of S, X S prime. Now all the sets except this collection C, those for the variables X prime S is 0 for those elements. So this is sum over this collection. This is C of S times X prime S, because other elements for other sets X prime S is 0. But this is for these elements, which are the sets picked, their corresponding X's value is at least 1 over F. This is less than equal to sum over S in C, C of S times F of F times XS. So this is F times summation S in C, cost of S times XS. Okay, but this is less than equal to F times opt. This is from here, that opt is greater than equal to this. So hence we have ALG by opt is less than equal to F. Hence the approximation ratio of our algorithm is at most 2. This concludes the proof. Next we see that how using this we can design a two-factor approximation algorithm for vertex cover. So what is the vertex cover problem? So if there is a nice reduction from vertex cover to set cover. So theorem, vertex cover reduces in polynomial time to set cover, and this will be a something called what is called an approximation preserving. Moreover, the reduction is approximation preserving. What do I mean by that? Intuitively speaking, if the reduction is approximation preserving, and if we have a alpha factor approximation algorithm for set cover, then using this reduction I can obtain an alpha factor approximation algorithm for vertex cover. So that is, if we have an alpha factor approximation algorithm for set cover, then using this reduction we can design an alpha factor approximation algorithm for set cover, for vertex cover. Okay. So proof. So let G equal to V comma E and K be any instance of vertex cover consider the following instance of set cover. For set cover, I need to say what is the universe. Universe is the set of edges E, E in E. Then what are the sets? For each vertex, so the collection of sets is, for each vertex, the set of edges incident on it is the collection of sets. So this is neighborhood of V, V in V, where NV is the set of edges incident on V, and the budget is K. So in the next class we will see the equivalence of these two instances and also explain why this is an approximation preserving reduction. Okay.